Algebra 2, state sample question number 17. Titanium-44 is a radioactive isotope such that every 63 years its mass decreases by half. For a sample of titanium-44 with an initial mass of 100 grams, write a function that will give the mass of the sample remaining after any amount of time and define all variables. Well, what type of function is this? If it starts with 100 grams and then after 63 years, it's going to be half that, so 50, and after 63 years, it's going to be then 25, and so on. This is a exponential function, or a geometric series here. It's going down a half each time. So the rate here is a half. But this is an exponential function called exponential decay because it's decreasing by half. And the formula we use for exponential function is a, or a of t, since we're doing a function of time, is the principal times 1 plus or minus r, the rate, to the t. Now the plus or minus is not there. If it's increasing, we'll use plus, but because this is a decreasing radioactive isotope that has a half-life, we'll be subtracting each time. So writing the function, well, again, we'll stick with that a of t, and that would be the amount of the mass remaining after t years. The p is the initial mass. That's sometimes referred to as the principal when we were talking about finance, or the initial. But this is the initial mass, so that's 100 times 1, and it's minus because it's decaying, half, and the rate is a half. So half at a rate is 50%, so that would be 0.5. And here's where it gets tricky. It's not just raised to the t, because it's not going down half every year. It's going down half every 63 years. So what we're going to actually have to do for our exponent is t, ugly t, over 63. Is time over 63, years over 63. And if you think about it, it kind of makes sense, because in 63 years, that will be 63 over 63, which is 1, and that would be, it'll go down a half. But like in 1 year, the mass is only going to go down a 1/63rd of that rate. So that's why we have to do a time over 63 for the exponent. So that's probably what would mess students up on this question. They would probably just do t there. And if you did and carried the rest of it out, you'd get a good amount of partial credit, but that's really what they're looking for. Now, they say define all variables. There's not a lot of variables to define, except that we're saying t equals time, that's another ugly letter there, time in years, and a of t is amount of the titanium-44 remaining. So we'll say amount of mass after t years. I'm writing really sloppy letters today. After t years. And when they say define all the variables, they really do want you to write that. That's not an optional thing. You wouldn't, if you wrote this, this is, this would be probably, there's a lot going on here, maybe a part 4, or, I mean, it could be a part 3, but it really should be a part 4. I'd say it's kind of like 2 points for this, and then 2 points for this, maybe 2 points for this, something like that. But realistically, this is probably a part 3, total of 4 points, and it's probably like 2, 1, 1, something like that. The rubrics are very vague on how the points are spread out, but I think you'd get a point for this, and then probably a point for defining things properly. All right, so then scientists sometimes use the average yearly decrease in mass for estimation purposes. Use the average yearly decrease in mass of the sample between the year 0 and year 10 to predict the amount of the sample remaining after 40. Round your answer to the nearest tenth. All right, they're calling it the average yearly decrease, but what this is really talking about is the average rate of change. And we have the formula for average rate of change, which is essentially the slope formula, really. F of, we could call it A or B. We'll say F of x2 minus f of x1 divided by x2 minus x1. And remember, f of x is basically y, so this is like y minus y over x minus x. The average rate of change is essentially the slope formula. But what we're going to be using this for is for year 0 and year 10. So f of year 10 minus f of year 0 divided by 10 minus 0. And remember, we always do the second minus the first when we do slope. It's the same thing here. So I have to figure out what these things are. Now, to really get a sense of what's happening here, maybe we didn't even really finish this up here. We got to finish this up here. And let's change this to a of t equals 100 times, instead of 1 minus 0.5, we'll write it as just 0.5, because that's what it subtracts to, raised to the t over 63. And let's take a look at what this function looks like in our calculator to get a sense of what's happening. Now, we know it's decreasing, so maybe we should have a little bit of a sense of what it looks like. But let's see, 100 parentheses, 0.5 parentheses, raised to the, it's going to have to use x instead of t, but that's okay, divided by 63. And we'll start with zoom 6, like how we like to begin. And I see the graph is working up here, working up here, working up here. It's spinning, 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 and it's done. I don't see anything. That's weird. Well, it's often that this is a 10 by 10 view. What if the graph is outside of this somewhere? So there are ways to find it. You could kind of think about, all right, well, if x is 0 or t is 0, where would this be? Now, if this is 0, this whole exponent is 0, and anything raised to the 0 is 1. So it's really going to be at 100. So that means this thing's hitting 100 all the way up here. And you could set your window, but let's try just zooming out and see if we can see something. And we're going to zoom out once, and that, certainly gives us a wider range, but even that I think is going to fall a little bit short because I don't think zooming out goes quite up to 100. So let's try zooming out one more time, and that's zoom 3. You can move that around to where you want to zoom out from, but I want to zoom out from the center, and there it is. And so that's the function. We see it is decreasing over time. So this is the amount of mass, and this is time. Notice that I don't need the space down here. You can work with this picture, but I'm gonna trim this a little bit. In my window, I don't need any negative y's, so I'm gonna cut that down to be 0. This way I just have that over here. And because x is time, I really don't need any of this negative x either, because that's like negative time. So once that's down graphing, I'm gonna cut that a little bit too. So in my window, I'm going to cut my x minimum. I could do 0, but I'm actually going to leave like negative 10, just a little bit of a space so that it's not right up against the side there. All right, but here is my function, and you can see that it is exponential. It is curving. It's not a straight line. It is a curve. And so let's just kind of bring this over here and have this as a reference in case we need that. But this is what's happening here. Find a place and just do a little sketch yourself. All right, let me put that over there for now. All right, but this is also helpful because in my table, I can figure out what f of 0 is, because that's just when your x is 0, what's your y, and so the answer is 100. So that would be 100 minus, I'm sorry, that's f of 0. I got to do f of 10 minus that. So f of 10 is 89.581. So 89.581 minus f of 0, which is minus 100, and that divided by 10 minus 0. And so let's see what this comes out to be. Clear that off. All right, let's do 89.581 minus 100, and I'm going to divide that by 10 minus 0, which of course is just 10. And I get negative 1.4019. Negative 1.4019. I think that's what it was. 0419. Let me fix that. 0419. All right, so what we just found was from f of 10, like say, this is our picture. How far is this? Well, if I take a look at my window, my x is going to 160. So 160, that's, that means that this is about 80, and so that would be about 40, and so this would be about 20. So from 0 to 10, that's like from here to here. So there's not a lot there, but what we just found was the slope of that change is about negative 1.419, and we do know that it is decreasing. So the issue now with the rest of this problem is they want you to use this, decrease rate to predict the amount of 40 years. Now, we are going to then, in this last part down here, compare this to the actual amount of 40 years because, again, look at my calculator. I could go to my table and scroll down to 40, or of course I can plug in 40 into my function to get what the actual amount is. But this can be used to estimate the amount because this is a slope thing, and because it's a slope thing, what we can use is we can use that slope to kind of use it like if this slope were to continue. Now, if I were to draw a little line here, I'll show you what I mean. That this is how much this graph changed in the first 10 years. But if it were to continue, it would come all the way down here. It doesn't continue at that rate. Again, think about it. In the first 63 years, it drops down 50. But in the next 63 years, it's only going to drop down 25. So that amount of decrease, kind of slows down. But using this, I want to use this to predict 40, and it's going to be wrong. And then I'll use the actual equation to get what it is 40, and they want to know, which one's greater, less than, so on. But the way I could use this is that is the slope of a linear equation. Remember linear equations, y equals mx plus b, and what we just found was the slope piece. So that'd be negative 1.0419x. And the b's, that's the y-intercept, which we know is 100, because that's where this starts at. So I can use this, and I'll use it down here. Y equals negative 1.0419 times 40 plus 100. And I could type that in to get a prediction of what the amount of mass remaining is. It's already in there, so I could just second answer times 40. And this is going to predict what is remaining after 40 years. And I'm getting 58,324. So the prediction is 58.324. But let's find out what it actually is. And the way we can find out what it actually is going to be after 40 years is use the function. I could do y, or I could do a of 40 in that function of 100 times 0.5 raised to the 40 over 63. And this is how we also could have gotten the values like f of 10 and f of 0, but we kind of just got lazy and you let our calculator do it. But this time, let's use the function. So 100 parentheses 0.5 parentheses raised to the 40 divided by 63. And the answer we're getting is 64.39. 64.39. I think this question said what's around to, this one said round your answer to the nearest tenth, so I should probably do that. This would be negative 1.0. Oh, no, that's not what they want rounded to the nearest tenth. They want this rounded to the nearest tenth. That would be 58.3, and this one is 64.4. So the final question. Is the actual mass of the sample or the estimated mass greater after 40 years? Well, here is our estimated mass, here is the actual mass, and the actual mass is greater. So the actual mass is greater than if you were to estimate it based on the slope from 0 to 10, because like we said, from the slope from 0 to 10, that doesn't continue on that slope. It keeps decreasing, but the rate of decrease slows down over time. So this is sample 17. There's a lot going on here. Average rate of change, I think, is something that could definitely come up, maybe in this context, maybe just simply what's the average rate of change between these two, x values or something like that. But an exponential function, knowing that it's decay, how to compare it. This is a great example of a Common Core modeling question. All right, that's it, guys. See ya.